Welcome to a marvelous Math Monday, everyone. I look forward to a lovely, terrific trigonometry week with you. Our schedule this week, we'll have a quiz on Wednesday that will mostly covers the topics that we look at tomorrow, as well as the topics today are the foundation for those ideas. And if all goes well, no, we're going to plan on a unit test on Friday. If we have to trim topics, I'd rather trim topics than ship the test back to next week. So we'll aim for this cumulative test on our knowledge from Monday to Thursday for Friday of this week. So welcome. Today we're taking a look at the primary trigonometric ratios first, and then the sine and cosine law in just a moment. So first of all, take a look at these problems here, sine 45, cos 120, and tan 235. And just make sure that when you use your calculator that you can get these outputs here. All right, go ahead and take a look at that and see if you can make this compute for yourselves. I'll pause the video. Definitely take a moment to try this on your own. You want to make sure that you can get the calculator to cooperate for trigonometry. All right, so are people able to get your calculators to cooperate for these sums? These are the answers that we want our calculators to output when we input these ideas. So when I push sine 45 and I push equals, I get something different than that. It's not the same thing that I'm seeing here. And I get like confused and frustrated and annoyed. I don't want to feel confused, frustrated, and annoyed all unit. I want to start this out now. So the thing that I need to do is switch this over to degrees. Make sure that your calculator is saying DEG and it's not in radian mode or gradient mode. I understand radians. I don't know really what G radians are talking about, so I'll figure that out. But in any case, now when I push sine 45 and I push enter, I get the required 0.7071 for sine 45. So there we go. All right, we're good with calculators. Let's see a thumbs up if you got your calculator work. All right, beautiful. Okay, good. Let's keep going. All right, now we want to take a look at Sokatoa. Sokatoa, not only is it the musical sensation sweeping the nation, but Sokatoa is a great mnemonic device you can use to solidify your memory of sine, cosine, and tangent. So you have some space on your handout here to fill in the acronyms and keep them in your notes here. So when we're talking about sine as so, what are we talking about there? So. Let's hear it, Rylan.
Sine opposite hypotenuse.
Yes, sine is opposite over hypotenuse. Good. Here is this is the angle of interest. We'll call this the angle of interest or the angle we're looking at. I'll often just call it the angle we're looking at. The opposite is the side opposite that, all the way over there. And if I create a ratio of this side and the hypotenuse, then that would be sine is opposite over hypotenuse. So here's sine. Sine looks like this. Is O over H. Okay, that's what we mean by opposite over hypotenuse. And then what about cosine?
Adjacent over hypotenuse.
Cosine is adjacent. Yeah. Great. And then tangent?
Opposite over adjacent.
Yeah, is the opposite. It's already there over the adjacent. Yeah. So the adjacent side is the non-hypotenuse side that's connected to the x. It's touching the angle. The opposite is the only side not touching the angle. And the hypotenuse is the longest side of the triangle. We can also recall that if I call this h here, and this a, and this o, that h squared would be equal to what?
A plus B.
Yeah, a squared plus o squared. The adjacent plus the opposites, the adjacent squared plus the opposite squared would give me the hypotenuse squared. And so this is just your Pythagorean identity, your Pythagorean theorem rewritten in the context of hypotenuse, opposite, and adjacent. So that's useful to think about. Now, we can later on, we're going to be taking a break from functions for this week. We'll be doing some ninja review of some past topics. But later on, we're going to be taking a look at the trigonometric functions for sine, cosine, and tangent. So we'll be coming back to this a lot over the course of this unit and the next unit. So we can use these ratios to find missing sides of triangles. So if I know this angle 67 degrees, what trigonometric identity could I use to solve for x? To solve one of these questions, name your sides. This is clearly the hypotenuse. What side is x? Is it the opposite or the adjacent? Yeah, this is the opposite. And then this side that's known is the adjacent. So if I know the adjacent and I'm looking for the opposite, what trigonometric ratio would relate adjacent and opposite to one another? Yeah, so tangent here is going to relate opposite and adjacent. So that's a great answer. So there, what I would do is I set up the equation. Tan of 67 is equal to the opposite over the adjacent. For the opposite, I have x. So there's my unknown in the numerator. And then I have a known denominator, 14. Then with some inverse operations, I can multiply both sides by 14. The reason I would do such a thing is because here my unknown is being divided by 14, so I'll use the inverse of division, which is multiplication. That will cancel this and allow me to go ahead and solve for for x. So there I will get x is equal to, and now I turn to my calculator and I punch 14 multiplied by, and I push tangent 67. And that gives me 32.98, so 33. And there we go. Circle it. That's your final answer. This is just what I punch on the calculator to give me that. Now, when I have my unknown organized in this way, here's my known angle. Now what's my unknown? What side is this? Here's my hypotenuse, and we're not worried about the hypotenuse for this question. My known angle is 30 degrees. What side is this? So here's my known angle right here. I know that's a 30-degree angle. Yeah, this is the adjacent. It's touching the angle, so it's adjacent to the angle, just in the same way that Julie sits adjacent to Rylan. We would say that this is the side adjacent to this angle. So this is my A, and my known side is the only other side left over. That's the opposite. So now I can set up an equation for this one, which looks like, let's use another color. I like blue. Here I would say that tan, again, I have adjacent and opposite being related, so I'm still going to be using tangent. And I would say tan 30 degrees is equal to my known side 4 over my unknown x. And now to solve this one, now I have a little bit more of a frustrating problem. I just have a little bit more inverse operations to do to truly isolate this x. So in order to get this x out from underneath this fraction, I can multiply both sides by x. But then I will have this problem over here of x multiplied by tan 30. And that I might find frustrating because I don't want to know what x times tan 30 is. That would be 4. But I want to know what x is. So now let's divide both sides also by tan 30. Now these x's are going to cancel. This x will be left alone because these tangents are going to cancel. And then I will have another line here that once I move my face, I will have space to write x is equal to 4 divided by tan 30. So that's what I will punch on my calculator now. So now I go clear and I say 4 divided by tangent of 30 equals, and this tells me it's 6.92, so we're going to go with 7. We'll round this to 1. This is what I punch on the calculator to give me this. Done final answer. And another thing that's important to do when you're imagining these questions, and the more you do this with simple questions, the more you'll be able to rely on this skill with more complex questions. The skill is check your answer by just visualizing these triangles and asking, does that seem to make sense? Here I have an angle of 30 degrees. That's less than 45. So I'm expecting that this side is going to be a little shorter than that side. If this were 45 degrees, it would be an isosceles triangle, and this side would be the same length as that side. Because this angle is shallower than 45 degrees, I would expect this side to be longer than that side. And indeed it is. 7 is longer than 4. So I can visualize a triangle, the side length 7 and the side length 4, and this might be a side length somewhere between 8 and 9. No, it's just a little bit bigger than 8. It's really close to 8. Anyway, this question here, let's take a moment to visualize it. Here we have quite a large angle, 67 degrees. That's a large angle for a right angle triangle. And just to review, we need a right angle triangle to be applying any of these laws, or to be applying these ratios. Here with an angle 67 degrees, that's very wide. You can imagine this is like a beam of light, and it would cast a very long shadow relative to the height of this flagpole. We would expect x to be quite a lot longer than 14 when we visualize this triangle, and indeed we got 33, more than twice the length. Oh, so let's keep going. We can also use these ratios to find unknown angles. So if I have a problem like this, where I have a 14 centimeter side, a 20 centimeter side, and an unknown angle, and I want to find this angle, what trigonometric ratio would I use to relate these two sides? What side is this? This is the hypotenuse. What side's that? Opposite. What trigonometric ratio relates opposite and hypotenuse? Yeah. So sine, right? So sine will relate opposite and hypotenuse. Again, right, if you want to know what you don't know, write down what you do know first. So I know that sine of theta is equal to the opposite over the hypotenuse. So 14 over 20. That would simplify to sine theta equals 7 over 10. That's an unnecessary step, but I just do that automatically. It just saves me a keystroke when I'm punching on the calculator. And then what I'll do, how do I solve this type of problem using my calculator? Suraj?
You use the reverse sign?
Yeah.
Like the inverse
So you're going to use the inverse function of sine, which is the sine inverse. So there, what you're going to punch on your calculator looks like this. The sine to the negative 1 of 7 over 10. And I already feel a little dirty because this is not sine to the negative 1. This is the inverse sine of 7 over 10. Recall that if I have a function f of x, we'll say f of x is equal to sine x, then the inverse function that would turn my outputs into inputs and my inputs into outputs is this. It is not an exponent. It's just a way of indicating that this is the inverse function of sine. So you're going to find that button on your calculator. It's usually the second function for your sine button, and it's going to be just over top of it. And this is what you punch to find the answer. So I'm going to push second function, sine inverse of 7 over 10, follow along on your calculator because you want to be able to solve these yourself. Sine inverse of 7 divided by 10 in brackets equals, and then I get 44.4 degrees. So here we go. Theta is equal to 44.4 degrees. And here I am writing over our last question. Oh dear. I'll erase that, put it up here. So are people able to get the same answer out of their calculators? Great. So if you're having trouble with that, I'll come around and we'll figure that out after the lesson. But make a note that you need to see me and we need to figure out your calculator together. Dave? Sorry? Sine 90 over 20. I'm a little confused of what you're, like if I can do some manipulation of this. So I could multiply both sides by 20 and have 20 sine theta is equal to 14. And then I could divide both sides by 14 to find 20 times sine theta over 14 is equal to 1. But that doesn't move me closer to an answer. One thing that's important to look at is in here, there are some brackets that are hiding here. And we want to remember something. Sine theta is just a number. And that right there is just one number. I can't put sort of stuff inside there or do stuff to the angle by dividing the angle or things. This together is one number. Sine will be some value, and it will always be between -1 or 1. You're almost always going to get a decimal answer on your calculator, unless the answer is 1, 0, or -1. Those are the only integers that sine theta could be, because it's always a ratio of this and this. So this will always be shorter than this, unless it's the same length. This one here. So this could be the same length as that. This could be a side length 20, and that could be a side length 20. But then it's just a 90-degree triangle with another 90-degree angle. It's just a line. It has no adjacent side. So we'll be taking a look at those when we start, actually tomorrow. But you want to remember, sine theta, that's just a number. And it will always be between 1 and -1. Okay, now we can look at questions like these, word questions, and solve these types of word questions with our trigonometric ratios. So what would be your first step when you're confronted with a question like this? You stand 57 feet from a building and look up at 55 degrees. How tall is the building? Sorry, Riley?
Nothing.
Riley?
Well, just look at this. You can kind of assume that it's a right angle triangle. Like it's going to have the 90 in there.
Did I say that the building is the Leaning Tower of Pisa?
No, but is it?
No. But even if I was talking about the Leaning Tower of Pisa, how do you measure its height? With a ruler. Not with a ruler. Like, would you measure its height along the side of the building? Or would you measure its height to the tallest point from the ground? Yeah. If you're measuring the height of a mountain, you don't climb the mountain and drag a string up with you and say that's how tall the mountain is. Because that's a diagonal. You would calculate the height to the summit from sea level, for example, maybe sea level, or maybe the roots of the mountain or the base of the mountain. And that would be a vertical distance. So we measure height vertically. If I lean against the wall because I'm very tired, and then I say, how tall am I? You don't make a mark on the wall and say, therefore, Mr. Jennings is 4 feet tall. No, I was really tired. I was leaning over very far. You would stand me up to my highest vertical height, then measure the top of my head. So here, yes, you can assume that this is a right angle. And the first thing that you would do, if you said, well, the first thing I would do, Mr. Jennings, is draw a picture of this darn building. That's great. You can even draw a window on it if that makes you happy. And then you can say, okay, I'm looking for this height here, and I'm going to label that height. I'm not going to label it H because I might get confused with hypotenuse. What can I label it? I will label it B for building. Okay, that's the height of this building. And then I'm going to draw this picture to myself. So I'm going to be looking up at 55 degrees. So I'm going to draw the angle of my sight here, and that's 55 degrees. And then, what else do I know? I know that I'm 57 feet from the edge of the building. So if it's 57 feet from the edge of the building and I'm looking up at 55 degrees, give me a guess. First guess, how tall would you think this building's going to be? And what you want to see when you're doing this whole guessing thing is first you guess, and then you test your guess with algebra and your trigonometric ratios. And over the course of the unit, your guesses are going to become better and your instincts are going to become better. Your instincts are going to become something with triangles that you can rely on to reliably check your work. So here, Siraj, what would you guess? You had your hand up?
I'd say around like maybe 75, 80.
Yeah, the 75 is a great guess, or 80 or something, and it's a range. Now, take us through your thought process, Siraj. How did you arrive at that number, 75, 80?
Well, if you're looking directly at the building from
Mhm.
57 feet away and you're looking 55 degrees up, that's just slightly, it's slightly over, like completely half, like 45 degrees.
Yep.
Meaning that it wouldn't be the same length as 57, so it would be slightly larger.
Mm-hmm. Yep. Yeah, so you're looking up 55 degrees. It's slightly higher than 45. And if it were 45, if this were 45 degrees, then the building would be 57 feet high. So you know it's going to be a little bit more than 57. That's great. So here we set up to answer. So we're going to put in our guess and even try writing down your guess. So as a class, we guessed 75 to 80. Let's see. Siraj gave himself a 5 meter or 5 foot margin for error. Let's see if he even got it in there. I think it might be. So what trigonometric ratio would I use to relate this known to this unknown? Tangent, good. So I would say tan 55 is equal to opposite over adjacent. TOA, T-O-A. Tan is opposite over adjacent. So I would say B over 57. And then go ahead and use your inverse operations. You're going to multiply both sides by this denominator. Multiply both sides by 57. And there is what you can punch on your calculator to calculate B. So B equals we just missed
81.4.
81.4. 81.4. So we could say 81 feet, 81.4 feet. Therefore, the building Now, let's just go back to that guess. Was our guess useful when we got this answer? If our calculator said that the building was 0.3 feet tall, would our guess have helped us? Yeah, we would have been like, there's no way that building 3.3 feet tall. It's more than a couple inches. If it said that the building was 600 feet tall, then we made some other mistake. So this guess confirms what our calculator is saying, and it helps us make connections between our intuition and your knowledge of the world and how things work, and how tall a building might be when you look up at it at a certain height, and you can connect that to the algebra. So it's making you a better mathematician when you're making these guesses. So good. Okay. Now, all of these ideas are really useful for solving triangles when they're right angles. But most triangles don't have right angles. A lot of triangles do. A lot of really useful triangles have these right angles. When we're looking at the slope of a line, we have rise over run, and rise over run are related by trigonometry. They're a right angle triangle. The slope of a line and its rise and its run. The heights of things, the shadows that a flagpole casts. The flagpole is making a 90-degree angle with the ground. So because of the way gravity works, we're often seeing these 90-degree angles in our world as well. But we don't always have 90-degree triangles, And that's where sine and cosine law can be very useful. So here is sine law. And sine law relates the side lengths of triangles to the angles that create them. And what it creates is three ratios that you can also flip. So I would like people to also write the flipped version of sine law. The flipped version of sine law looks like this. A divided by sine A is equal to B divided by sine B is equal to C divided by sine C. Okay? Now, in order to use sine law, I need to understand that this side length here is related to this angle. This side length here is related to that angle. In fact, this angle, in many ways, creates this side length. As angle C opens up, the distance between my fingers gets bigger. That side length C gets bigger. So, as sine is 0 when the angle is 0. When the angle grows to 90 degrees, sine gets to be its biggest. That's when sine is equal to 1. So that's when the angle is getting larger, sine is increasing, so that increases the length of that side. So you can imagine, just sort of put that into your imagination and see this side C opening up and creating this line C and making it bigger. So I can use sine law to find unknown sides as well. And here I have a triangle that has no right angles in it, but it has a 73-degree angle and a 42-degree angle. Let's just review. What's the angle of side C?
180 subtract those two.
Right. So Rylan is telling us that angle C is 180 minus 73 minus 42. So what is it then? Drea?
65.
Yeah, good. So 65 degrees. Now, we didn't need that for the problem, but I just wanted to remind people that the sum of the interior angles of a triangle is 180 degrees. That's an important law. When you have your 90-degree triangle, that's very useful because the other two angles will add to 90 because you've already got half of your 180 there in the other corner. Okay, so now we can use sine law here to find this unknown side AC. And so, if I want to know this length of side AC, let's call it side B. Oops, that's a D, Mr. Jennings, because you used to do that in grade 1. You still do it apparently. B. So this side length B, we'll call it side length B. And there we would use sine B over B. So we can write it that way. But I like to have, do you like to have your unknowns in the bottom or in the top? Did you say it makes no difference, Riley?
No, I'm just saying it means like I will do whatever.
Yeah. It can work when it's on the bottom, no problem. It's going to work. You're going to be able to solve it. I find it easier if it's just on the top because I have one inverse operation to do rather than three. So rather than using this one here, I use this one here. So you can flip the whole thing first when you set up your equation. So let's use this idea here. We'll take one of these pieces and we say B divided by the sine of B, which is 42, is equal to this known side here, BC, divided by sine 73. And I'm just being strategic because there, when I multiply by what I'm dividing by, I'm just going to multiply here by sine 42, both sides. This already gives me what I need to punch on my calculator with a single inverse operation. So it's just a little bit more elegant than having it flipped in the beginning and having to move things around 3 times to get it isolated rather than just moving one thing once. So what is side B? This is what I punched on my calculator. I go 23 multiplied by the sine of 42, and then I'm going to put equals is 15.3, and then I divide by sine of 73 equals 16.09, so 16.1. So we'll say B is equal to 16.1. And now there's one thing that we could have done before we started this problem, that would help us evaluate that answer. We want to guess. So when I look at this, side length B, is anyone surprised that that's around 16 meters? Here we have a large angle, which opens up onto a side length of 23. Here we have a smaller angle, so we would expect that to open up less, and it's going to open up onto a smaller side over there. So when I get this angle 16, I'm not surprised, because that seems to be about the right relationship between 23 and this number that we have. Thank you very much. That's very kind. So that's how we use a sine to solve these types of things. And then here, we can also use this to find unknown angles. So here we've been asked to find angle P. So let's take a look at this problem over here, angle P. Now, again, we can guess. If this is 39 degrees and it's opening up onto a relatively short side, 28, we have another side here, 41. Can I go ahead and calculate this unknown side right away? Not yet. I can't use a Pythagorean theorem because I don't have a right angle triangle here. I might. I mean, one of these angles might be 90 degrees, but I have to prove it first. It's not been told to me yet. So I can't calculate this unknown side length, but I can still find this angle P if I find angle R first. So let's label our angles. This is angle R, and this is what we're desiring is angle P. Okay, so we'll call that X. Well, it's just, no, we don't need to call it X. It's already called angle P. So we'll just call that P. Now, to answer a question like this one, we're going to use sine law, and we're going to use it to find an unknown angle. So let's set that up over here. Now my unknown is an angle. I'm going to put my unknown on top, and I already have one pair of sides. Side Q is related to this side. This 39 degrees opens up a side length of 28. So let's use this and this ratio here. This angle R is opening up an even bigger side of 41. So what do we expect this value of angle R to be? Would it be bigger than 39 degrees or smaller than 39 degrees? Yeah, it's going to be bigger than 39 degrees. It opens up a bigger side on the opposite to it. So when we're making these guesses, it forces us to imagine the way sine law works. And it's going to help your intuition reinforce that law for you in your mind. So here, I set it up this way. Sine 39 divided by 28 is equal to, well, this angle R opens up onto 41. Note, I want to find this one, but in order to find that one, I need to find this one first. Because I don't know this side, but I do know that side, so I can find this angle. Once I have this angle, I'm going to do that plus that is equal to this minus 180. So let's set it up that way. And then that's equal to the unknown angle, sine R, over 41. Then we go ahead and we're going to do our inverse operations. Multiply both sides by 41. And that's going to give us what we want to punch on our calculator. Well, very nearly. 41 over 28. Actually, give me a little bit more space than that. Write this in a little bit deeper into your page. Here, like this. 41 over 28 times sine 39 is equal to sine R. But I actually want to know what R is. So what I'm going to do is put all this in brackets and take the inverse sine of that. And that way I'm taking the inverse sine of both sides, which is going to isolate my angle R. So this is what I punch on my calculator. So I'm going to push second function, sine inverse. I'm going to create a bracket. Then I'm going to do 41 divided by 28. And then I'm going to multiply that by sine 39. Finish my brackets, push enter. And then I get an answer 67 degrees. So am I surprised when I get an answer 67 degrees for angle R? I'm happy with that because it corresponds to my guess. This angle is bigger than 39. It's opening up a bigger side here. So that's congruent with my intuition about these triangles. Now I can use angle R to calculate angle P. So P plus R plus Q is equal to 180. Great. But I have two knowns here, Q and R, and I just don't know P. So P is equal to 180 minus R. R was 67. And minus Q. Q was 39. So P, therefore, is equal to... Did you say 34?
74.
74? Is that right? Looks right.
I think so.
It is right. I think so. Yeah, 74. 74 degrees. So there's our answer. And that's how we can find an unknown angle using sine law. And here we had an extra bit of doing to do because we needed to go by way of calculating this one first and then that one. Now that I know all the angles, could I find this missing side length? Sure, I could use sine law or cosine law to find that missing side length. Let's keep going, everybody. Now we get to cosine law. Cosine law looks a lot more complex than sine law, but if you remember, a squared equals b squared plus c squared is your Pythagorean theorem, you'll find that that's already baked into your cosine law. Cosine law, a Pythagorean theorem is just a special case of your cosine law. If I have, here I have A, B, and C, when this is 90 degrees, the cosine of 90, go ahead and type cosine 90 on your calculator and see what you get. What do you get when you push cosine 90? 0. So what's anything 2bc multiplied by 0? 0. So since this is 0, when this angle is 90, you can understand your Pythagorean theorem as a special case of cosine law. And then all you need to remember, if you're memorizing cosine law, is that 2bc cosine A is this extra bit that we have to add into this, this to create a trinomial. We'll notice a squared, and then a 2bc cos A. So that is actually a trinomial there. So we just need to remember this term. So we can use this to solve for unknown sides and to solve for unknown angles. If you're given the three side lengths of a triangle, you can't use sine law to find any of the angles because sine law, you always need an angle known already to solve these. But with cosine law, we can use this to solve for unknown angles. You'll notice over here, the formula has been rearranged. All we've done is we've shifted this to the other side of the equation, shifted that to the other side of the equation. So that's why this is a minus. And then we divided by the 2bc, and that isolated cos A over here. This is the same thing as this. It's just inverse operations have been applied to it so that we've isolated the angle. So that's how you would solve questions like this. Now, with this question, we can use cosine law to solve for this unknown side. We don't know. The first thing that we're going to do when we're trying to solve triangles is ask, is it a right angle triangle? This is our flow chart. Is it a right angle triangle? If yes, use your trigonometric ratios. You don't need special sine law, cosine law. If it's not a right angle triangle, then you go looking, can I use sine law? Because sine law is much simpler to use than cosine law. Here, I look, and when I'm looking to see, can I use sine law? The thing that I want to see is that I have some pair of angle with opposite side known. If I have this pair, I can usually set up a sine law to solve for other unknowns. In this case, notice that the known angle looks down onto the unknown side. So there, I cannot set up sine law as a productive way to solve this question. I need to use cosine law. That's my stages of thinking to go through to do this. And I can still make a guess when I'm looking at a question like this. So just let's use our intuition and we'll put in a guess here. If we have an angle opening up 37 degrees, it's less than 45, but it's more than 0. It's quite close to 45, but not quite there. And it's staring down a side length 11 and a side length 8. what would you expect this side length to be? Would you expect it to be between 11 and 8, less than 8, or more than 11? What would you guess this side length to be? Dave?
Less than 8.
A lot less than 8 or a little bit less than 8? Would you guess it to be like 2 or 7? Because those are quite different.
2. No, 7.
Closer to 7, eh? Okay. Siraj, what were you thinking?
I was thinking around 5-ish.
Yeah. Riley, was that a guess or a stretch?
It's a little bit of both, actually. I was stretching, but it could be a guess.
What's your guess here?
I was thinking, I don't think it's going to be like exactly 2, but I think it's going to be closer to 2 than 7.
Oh, okay. So we've got guesses here ranging anywhere from 2
Like, purely
to
based off,
7.
like, looking at the shape. I don't know if, like, all the lengths are actually
Yeah,
accurate.
are these to scale or not? Yeah, we're not sure, but they look pretty good. If this is 11, that could be 8, and this looks to be about 37 degrees, so sure, yeah. And you think that would be about 2, eh? Let's refine your guess a bit. If I divide this up, there, each one is 4, right? I didn't put this one in the right spot. It should be down here a bit, so I'll put this one a little higher. There. And so that would be about 2. That's 2 there, because I divided this 8 into 4. If I reflect that down, I think it's only going to about there. So to me, I think Siraj's guess is about the best, like looks to me about 5. If this is to scale. If it's not to scale, actually, I was thinking more closer to Dave's guess, like around 7. But it might be more than 8, but it wouldn't be much more than 8. Now, let's do the math. We spend a lot of time talking about those guesses. Let's do the math now. And we'll do this in black color. Okay, so the way I set this up is I first move my face off of the law that I need. And then I come down here. I'm going to use here. I want this to be my main thing that I know. I can use cosine here of the known angle. So this is my known angle. So that's what I'm going to put in there. And the opposite side here, the angle opposite to that is the one that I use over there. So here I have a squared is actually c squared. So this might be a little confusing to set it up, but you have to think through this every stage. Anyway, you have to say, this is my side that's opposite the known angle. Here's my known angle over here. And this is equal to 11 squared plus 8 squared minus 2 multiplied by BC multiplied by 11 multiplied by 8 and then multiplied by cosine of 37 degrees. Don't let these letters fool you. They are arbitrary. Here we have this known angle C. It's opposite this unknown side, and that's the side we would desire, we would like to know. This is what I punch on my calculator to find C squared. So if I take the square root of all of that, then that's going to give me C squared. But let's do this in a line. This is 121 plus 64 minus 2 times 11 is minus 22. 22 times 8 would give me 176. So this is minus 176 cosine of 37 degrees. I can punch that on my calculator, no problem. I could do this addition first as well. 121 plus 64 gives me 185. So this just simplifies what I'm punching into my calculator. Now remember that cosine can be at its maximum 1. That's its biggest value. And so this is going to be something smaller than 176 when we punch it on our calculator. 185, I punch on my calculator. Minus 176 times cosine of 37 equals. And I get 44.44. All right. Is that the length of C? C is 44, and our guess was really wrong. Our guess is really bad, guys. It's 44.44. Yeah, how do we do that? How do we create a side length of 44 with another side of 8 and a side of 11? Because it seems to me like even if those were as wide apart as they could be, that would only be 19. Faith? Yeah, so I have to take the square root of both sides still. So here I know c squared now. Now I take the square root of both sides. I don't need a plus minus because this can only be a positive value. So take the square root of what you've got on your calculator. And we get 6.66634. Cool. Very close to 5, even closer to 7. So our guesses were good. Our guesses were helpful here. C is equal to 6.7. Cool. That's how we solve for an unknown side using cosine law. And my goodness, we're going to be able to finish this lecture by break. We have one more problem to do, and that's for solving for unknown angles. If I want to solve for an unknown angle here, I would set this up this way with cosine law. Okay? So I might need a bit of whiteboard, or maybe I can do this just over top of this problem. I'll just move my face over here. There we go. So here, now we can still guess, right? What would you guess this is? This is an angle. It's opening up onto the longest side of a triangle, but the side lengths are all fairly close, 8, 6, and 9. Would you guess this to be 45 degrees, 90 degrees, or 120 degrees? Dave says 80. That's like a really sharp guess. It looks really close to 80 to me. I think that's a really great guess. People see kind of why Dave would say 80 degrees. Why would you say that, Dave? Dave, why would you say that?
It's almost 90, but not quite.
By this diagram, right? If this is a scale diagram, we would say it's about that. Yeah, it's cool. All right, let's try it. So here, let's set it up this way, where we're going to say cosine of z is equal to b squared plus c squared minus this squared. Okay, so this is our b, this is our a in the problem, and this is our c. These are our sides. Because these sides are the corresponding angle and side. So this here corresponds to this one in the formula. So I have to make sure that I get those right, because I'm subtracting that one, I'm adding those ones, and I multiply those ones on the bottom, but I don't multiply this one on the bottom. So those are all important things to think about as I set this up. So the cosine of z is equal to 6 squared plus 8 squared minus 9 squared. So that's a known, so I can put that in there. All divided by 2 times 6 times 8. Okay? And this should always give us a value between -1 and 1. Because this is a triangle that exists in our dimensions. If we had a triangle that was impossible, it might give us a value that was bigger than that, and then your calculator would say, I can't give you a cosine that will do that, meaning I can't give you a triangle that has those dimensions. But this triangle is possible, so we should be able to get an answer. This would be equal to 36 plus 64 is 100. 100 minus 81 gives us 19 on the top. 19 divided by 2 times 6 times 8 is 12 times 8 is 96, I think. 96? Yeah. 19 divided by 96. 19 divided by 96. So then that's my cosine of z. Cos z, okay? So now, if I know the cosine of z is 19 over 96, I use the inverse cosine of both sides, and that way I will get a line that looks like this. I'm going to do it in another color because I'm kind of running out of space, because I really tried to give you a one-pager today. So I'm going to zoom in so I have more space to write. It will give me this line here. The z is equal to the inverse cosine of 19 over 96. That's what I punch on the calculator to solve this problem. Okay, so z equals, so I push cosine inverse. I put this in brackets just like you see it there. I have a bracket, 19 divided by 96. I end the bracket and I push equals. Tells me 78.58. 78.6. Dave, how you feeling about your guess? Huh? Good, I guess. So the way I hope you feel when you get an answer like 78.6 and your guess was 80, I want you to be like, yeah, I have a good intuition for triangles, and I can do the algebra correctly. I'm feeling good about this unit. So I hope you're feeling good about this unit after you complete some practice problems in the textbook. Page 220, it's prerequisite skills on sine law, cosine law, and your trigonometric ratios. And there's a delta math as well for more practice. If you're bored by any of that, try some of the challenge problems. I assure you they're not boring. they're very interesting. I was on the weekend. I found this YouTube channel. Well, I reviewed a YouTube channel that I enjoy that looks at challenging problems, and I stole a lot of these from that YouTube channel. And my wife was like, "I'm ready to watch a TV show." She doesn't call me Mr. Jennings. She says, "Hey, I'm ready to watch a TV show," and so I turn off the video and we're watching the TV show, and I'm trying to do this question in my head, and it's just bothering me so much. And then she runs to the bathroom. I get the paper out, and I'm like scribbling numbers. So I find it interesting. I hope you do too. And definitely, if you have questions with any of the material, come find me by email or raise your hand and ask me a question. And I hope your math practice is very fruitful today. Bye for now, everyone.
What were the texts